Okay, so good morning, everyone. So, welcome back to Big Data Analysis class. Okay, our first lesson this morning is about model assessment. Can you also check this slide in Lentera? Okay, so some material of this slide you can check in my website about tutorial and bootstrap something, and the rest is from the book of Christoph on data mining. Okay, so these are the topic that we will discuss in the first slide. Okay, so first is about bias and variance dilemma, and then we talk about mean square error, and then confusion matrix, the one that you already actually familiar with when you practice WEKA last time. Okay, so last time you asked, what is that? What is the meaning of resampling and so on? Okay, so and today we'll discuss about that more detail. So, okay, so what is model error? Model error is basically the difference between the observed, the true value, okay, and the model output value. So if you have a certain value that is actually true, okay, and then now you create a model, okay, the output of that model is called the model output. Now, the difference between the true value and the model output is called model error. Okay, so we can express model error in many ways. Okay, so one is usually we use as absolute error or square error. Okay. Now, when we say goodness of fit of the model, so when we do calibration, so we try to reduce the error, okay, between the model and the observed value. Okay. And then in validation, we call this as prediction error. So now, when you do a model, okay, sometimes we have what is called overfitting or underfitting. What is overfitting? Overfitting means unnecessary increase in model complexity by increasing model parameter or degree of freedom. Okay, you don't want to have a model that is overfitting. Why? Because it will increase the model variance. Okay, at the same time, you also don't want the model to be underfitting. That means your model is too simple that do not fit the data. Okay, so the term bias is basically error that cannot be reduced by increasing the sample size. Remember when you practiced WEKA last time, okay, you try to increase the sample size up to a certain point, okay, that error cannot be reduced anymore. So this is basically what this bias is about. Okay, so this is a systematic error that is the difference between the estimate expected value and the true value. Okay, so bias here is the difference between the true value and the expected value, the estimate of the expected value. Now, on the other hand, we also have what is called variance. So this is an additional error to the bias that incur because of the sensitivity to the random fluctuation. So this is where your luck is about. Okay, random fluctuation is basically about luck. So this is what is called random error. So remember, we have two things. One is called bias, which is systematic error. The second one is called variance, which is random error. Random error is basically about luck. Okay. Now, this error can be reduced by increasing the number of sample data. Okay. In bias, you cannot reduce that error by increasing the sample size. Okay. Now, one measurement of error is to use what is called square of mean difference between the true value of one parameter and the estimate. So the estimate, we put the caret symbol here. Okay, so E represent the expected value, means the average. Okay, so this is the estimate value from the model, and this is the true value. Okay, you minus that, and then you take the average. So basically, MSE is basically what? The square of the bias and the variance. So here is what is called bias variance dilemma. So there is a trade-off between the bias and variance. So for a given MSE, it means square error, large bias mean small variance. Large variance mean small bias, right? Because you see here, the formula is MSE equal to bias plus variance, right? So we want to find a model parameter that neither too complex, which is overfit with the data, or too simple, which is underfit with the data. So basically what we want is to minimize the MSE value. Okay, so suppose this is your model complexity. Okay, so what I mean by model complexity is very complex model will have a very sophisticated function, a lot of number of parameters. Okay? And in this y-axis, okay, we have error. You will see that the bias, okay, will actually reduce, okay, significantly as you increase the model complexity. Okay? While the variance will actually increase with the model complexity. So the MSE is just bias plus the variance. So this red one is the MSE. So our goal is to find the minimum MSE. Okay. Now, this is your fitting, okay, compared to the model complexity. Okay. So if your model is very complex, okay, so we have what is called overfitting, meaning, for example, example of overfitting is like this. In regression, you use polynomial of very high degree, for example, degree 6, degree 7, and so on. Okay. Of course, your line will overfit. That means your line will exactly match with all the data points. Okay. So this is what I mean by overfitting or of increasing the model complexity. Okay. Underfitting, on the other hand, if your data is actually, for example, quadratic, right? But you are putting it as a linear model. So in that case, you are underfitting. So our goal again is to maintain the minimum MSE, okay, which is to have high bias and low variance. Okay. Now there are four types of possible error. Okay. Four type of possible build in here. Yeah? So there are two type of error. One is the error of commission. The other one is error of omission. Okay. Where the build here is, okay. So say you have selected option. Okay. When it's exactly correct, so build and build, so you get the correct choice. Okay. If they are not correct, so you can have either error of commission or error of omission. So can I put it this way? So this is what is called confusion matrix, yeah? Or sometimes we call it contingency table or misclassification matrix. So uh, first you will see this is your hypothesis, okay, the truth value. Okay? Say the truth value is positive or negative, right? The test result is either also negative or positive. Okay? So of course, when the truth is positive and the test result, your model said positive, okay? So we call this true positive, TP. That is exactly no error, right? So correct result. The same thing here, if the truth is negative, okay, the test result is also negative. So again, you have true negative. Again, this is no error. Yeah? So we call this TN, yeah? True negative. This is exactly this one. So not build and appropriate option is also not build. So these two are the correct choices. Okay. Now, if the truth is positive, okay, and the test result is actually negative, so you have what is called false negative. FN means false negative. So in statistics, we call this alpha, okay, or type 1 error, or sometimes we call this rejection error. Okay, so this is the first type of error. The second type of error is called false positive. What is that? When the truth is actually negative, but you perceive that in the model as positive. Okay, so FP means false positive. In statistics, we call this beta. Okay, we call this acceptance error or type 2 error. Okay. Of course, when you sum all of this, okay, a false negative and true positive, when you sum, you get P, which is the true positive. So look at this diagram. Okay, this diagram represents this. Fn here is false negative. TP, okay, is true positive. Okay. If you add the two of them, you will get the P, which is the total true positive. Yeah? The same thing here. Okay. True negative Tn, okay, plus the false positive Fp. If you add, you will get the true total true negative. Okay. Now using this diagram, okay, we will use to compute many things. Okay. So this is the graph between the alpha, okay, error of commission, which is false negative, with the error of omission, which is false positive, beta here. So when you plot this diagram, okay, if you get both sides, yeah, true positive and true negative in your model, and later on you plot, okay, if you put the random guess line here with this straight line, okay, so this is represent just guessing. Okay. Now, if your model is actually in this blue side, of course, this is much better than just random guessing. Okay. But if your model is a kind of red like this, so this is meaning you have a better judgment on your model. Yeah. Of course, the ideal case is no error, right? So zero error commission or zero error omission. Okay, so so if you have a two distribution, okay, so this is the normal one, the blue one, and then the red one is abnormal. Okay, so what is true positive? True positive is this region. Okay, what is true negative is this region. Okay, while the error, okay, this is called false negative, and this region is called false positive. Okay, so of course your goal is to find this threshold, okay, as you move this threshold to the right or to the left. Okay, so that you can get the balance between the two error. Okay. Of course, if the two curves are really separated, then you get zero error. Okay. Anytime if you have a question, you can ask. Okay. Don't hesitate. Now, based on that true positive divided by the total positive, right? So we have what is called index of sensitivity. So sometimes we call this recall or hit rate, okay, or TP rate. So what is this? This represents how often we will find what we are looking for. Okay. The second index that we can also derive from this simple diagram is the true negative divided by the total negative. Okay, so this index is called specificity. Okay, so that represents how often we will find what we are not looking for. Okay, so this is the other way around. So, and based on those two, okay, we can also calculate the other indices. Nah? So 1 minus specificity, okay, is called FP rate. Okay? And then accuracy can have two types. Okay? One is based on sensitivity and specificity. And then second type of accuracy is computed by the true positive divided by the total data. Okay. And sometimes you will use these indices to retrieve the document. So in that case, we have several other indices that we can use. So when we said retrieve, that means TP plus FP, true positive plus false positive. And when we said precision, that means TP divided by TP plus FP. You remember TP means true positive, FP means false positive. Okay? So all these are the indices that we can actually compute. The same thing, we have other indices like F measure, FTR, and so on that you can actually use also. Okay? Now, if you look at the WEKA's result, you can see all these indices there, right? And then the one that I provided here is the formula to compute those indices so that you will understand where it comes from. Okay? So, we can also plot between the precision and the recall. Recall means the sensitivity. Okay? So, but be careful here. Okay? What you need to do is to check where is the ideal case. The ideal case in this case is 1 and 1. Yeah? So here, not at 0. Okay? So in that case, when your graph is actually closer to the ideal case, that is the one that is better model. Okay? Okay, so suppose you have indices of confusion matrix, okay? They come from WEKA or from other means to compute. Say this is your test result. Okay, so you have four classification A, B, C, D, and this is the truth. And on the column is the test result, and these are the value. Okay, can you calculate all these performance indices that I mentioned above? Okay, so for your practice. Is it possible to compute say for example, you compute this sensitivity, specificity. Can you compute? Can you compute the FP rate, accuracy, 1 and 2? Okay, relevant, retrieve precision. Can you practice that? Is there any difficulty? So basically what you need to do is from the confusion matrix, okay? So you need to calculate which one is the true positive, right? The true negative, false positive, false negative, okay? So when you have a confusion matrix, you calculate first the Tn, okay, Fp, yeah, the one that we discussed a while ago. So Fn, Tp, Tn, and Fp. Okay, so that is the one that you need to calculate first. Okay, this one. So when you have a confusion matrix, okay, that we have earlier, this is our test, right? So how do you get the value of true positive? What is the correctly classified in this case? The correctly classified is in the diagonal. Okay, so 4 plus 7 plus 2 plus 10, that is the correctly classified. So this is the TP, okay, 4, 7, 2, and 10 is the true positive. Okay, so what is the P? P is the sum of column, yeah, this one, 7, 7, 3, and 10. Okay, so the same thing here, the N, okay, is the sum of sum minus the P, which is the sum of column. Yeah? So, and then the Tn, okay, is the N minus the sum of the confusion matrix, okay, minus the Tp. Okay, and then you can calculate the Fn, which is P minus Tp, and then Fp is N minus Tn. Okay, after that you can calculate the sensitivity, which is Tp divided by the P, and then specificity, which is Tn divided by N. Okay, so I think in the back of the slide, okay, that is the answer there. Can you check? So is there any question about this? So you see here is, for example, insensitivity, okay? So class A, right? Can you see? I'll put here with this. Okay, so if you look at this, okay, look at the diagonal, okay? So 4, 7, 2, and 10, right? So in that case, you will see 4, this one, divided by 7, okay? And then this one is 7 divided by that 7. And then 2 divided by that 3, okay? 10 divided by that 10. So you can get that sensitivity. Okay? So the total is 27, so the accuracy is just the correct one, which is in here is 4 plus the 20. Okay, so we have 27. So how much is the correct result? 4 plus 7 plus 1 plus 10, how much? Hmm?
23, sir.
23, right? So that is the one that you can use here. So for my case, I created this code in MATLAB. Wait, I'll show you. Can you see my screen?
Yes, sir.
Okay. So here is our data a while ago, right? This is the confusion matrix. Okay. And then we calculate the sum of row, and sum of column. Okay. So, and then I just fill up this confusion table. Okay. And then we can calculate the correctly classified, which is the sum of the diagonal divided by the sum of sum. The sum of sum is 27, right? And then we calculate this TP, which is the diagonal of the confusion matrix. So basically this is the true positive. Yeah. Okay. And then the sum of column is the positive, right? And then the sum of sum, it is 27 minus P. Okay. So you will get the negative. Okay. And then Tn is just this n minus the sum of the confusion matrix. Okay. I transpose this and then minus the Tp. Okay. And then here we can calculate the false negative is just P minus the Tp. The same thing with the Fp. It is false positive. It is just n minus Tn. Okay. After that, everything else is just based on that formula a while ago. Okay. So here, if I run this, okay, so I can also calculate the ROC curve. Can you see the ROC curve? Maybe I should share the whole screen. This is the ROC curve. So if you look at the points here, okay, I just put a line. So these are the data that we put in the ROC curve. Okay, so which is based on what? Sensitivity and 1 minus specificity. Okay. Now we come back to the slide. Okay, we have the next point is to calculate what is called receiver operating characteristic, or ROC. Oops. Yeah. Okay, so again, this is on the axis of vertical axis. We have sensitivity or TP rate, and then on the horizontal axis we have 1 minus specificity. Okay, and then what we want to get is actually the area under the curve. Okay, now say you have two model A and B. Okay, so the most important part is you need to know which model is better. Okay, so in this case, you check the ideal model. The ideal model is in this point. Okay, and this line means random guessing line. Okay, so if your model is closer to the random guessing line, that means your model is not that good. Okay, if your model is actually close to this line of ideal model, then this is actually better. So in this case, you will see A is actually better than B. Okay. Okay, up to here, is there any question?
Sir, sorry to bother, but how do we really determine the ideal model? Is it always the same for like ROC curve? The ideal model will be on top left corner.
Yeah, if ROC curve is in the top left corner, if based on this is good question, yeah. So look at this earlier. Can I share my screen again? So that depends on your variables. Okay, the ideal model that depends on the variables. Okay, so basically, if you are using ROC curve, okay, the ideal model must be on the top left corner, right? But if you are using this earlier curve here, okay, so you know the ideal case, if you are using precision and sensitivity, the ideal model is on the top right corner. Okay. But if you are using this one between alpha and beta, so the ideal case is 0. So basically, if you are looking at this, what is the meaning? Of course, the ideal model means 0 error, right? So, and if you look at the formula on these things, right? So that is the one that determines the ideal case, because this is meaning of 0 error. Okay? Look at the formula of sensitivity and precision, right? So precision is TP divided by TP plus FP, okay? And then the sensitivity is TP divided by P. So of course, from there you can see basically what we said as ideal model is no error. Okay, we just play with the formula. Because of that formula, then you will see where is the ideal model. So now depending on the chart that you are doing, okay, so if it is precision and sensitivity, the ideal case is in here. If it is ROC, the ideal case is in the top left, right here. If it is a error between alpha and beta, so the ideal case is the bottom left, and so on. Do I answer your question?
Okay, sir. Thank you.
Yeah, okay, very good. So is there any other question? Okay, so if not, I will go to the next topic, okay, with this resampling method, okay. So, in model selection, basically, when you run WEKA last time, you practiced already, right? And then I asked you to try many different model that you can try, okay? So you find a model with the right complexity without overfitting or underfitting, okay? So for that, I would like to ask, last time I asked you to do what is called cross-validation, yeah? For example, 10 or 5, right? And then now I want you to understand what's the meaning of that, okay? So, of course, you already know how to compute the model performance. Basically, the software will calculate for you, right? All this misclassification error, accuracy, sensitivity, and so on, right? So now I would like you to understand, okay, what happens if we use all the data as training sample, and then we do what is called hold out method, and then cross validation and bootstrap, okay? So for that purpose, I would like to explain as follow, okay? Say, if you have all the data that you have, say you have 100 sample data or 1,000 or 1,000,000 sample data, okay? The n or the number of sample does not really matter, okay? So now, when you use all of our data as training sample, okay? Now, what will happen? Even if you get 100% correctly classified, okay, you will never know if the model is robust enough to predict the previously unseen record. So this is what is called the worst scenario of training without testing. Okay? Why? Because it's susceptible to overfitting. Okay. Now, another method is to do partition of the data into two parts. Okay. One is called training data set. The other one is called test data set. Okay. So let me draw something like this. Maybe I need to put it in the whiteboard. Say, this is your data, okay, the whole data. Yeah. So this is your table 1, 2, until n. Yeah? N can be 10, 100, 1 million. Yeah? It doesn't really matter, right? So n is the number of data that you have. This is suppose your table. Okay. So now in this table, you want to separate, okay, using whole out method. One is to train your data set, and the other one is to test your data set. For example, you said, okay, half of your data, okay, this one is to do training. And then this one is for testing. What is the meaning of training and testing? Okay, so the meaning is like this. So you only use this part of data that is for training. Okay, say for example your y equal your model is y equal function of x, right, comma alpha, right? This is your model. Okay, so this is your input, this is your output. Yeah, your y is something like this. So let me draw. So this is your x. This is your y here, right? And then when you say training, what is the meaning of training? You give the input, okay, of x and y. Right? Training means you have x and y, and the function, you want to get the parameter alpha. In regression last time, we already used this. Yeah. So you have the data with this x and y, dot, right? And then what you will do, you will create the line, right? Okay, this is your model. The function is linear. So what is alpha in here? Alpha, in this case, is the m and c, yeah, which is the gradient and the slope. Okay, is this clear now? So when you say training, that means you have the input and the output and the function, okay, and then you will get the parameter. Okay, you already did that, right? But when we said, look, if you use the whole data, and last time you used the whole data, right? When you use the whole data and then you do training, you get the parameter alpha, and then you use that to predict, right? What do you mean by predict? Predict means I have my x, I have my f, and now I have my alpha. I want to calculate my y. Yeah? So I have my input, I have my model, right? And then I have my model parameter, alpha in here is the slope and intercept. Now I want to predict what is the output, right? That's the meaning of prediction, right? So when you do this, what will happen? Okay, yes, based on this data that you train, of course, it will give you very good result. Say you get 100% correct. Okay, but this is called overfitting. Why? Because if you have new data, okay, you're not sure. You're not sure that the data that you have trained, that you have calibrated, can actually predict correctly or not. Okay, so how to overcome that? Okay, then what you need to do is to validate. How do you validate? Okay, to validate is to create what is called test data. So say your data is n, right? And then you don't use everything, okay, for training to calibrate that. So you only use a portion of your whole data set for training. Okay? And then, what is this test data? Once you train, okay, the X is here. You put it inside. This, for prediction, you don't use the training data. For prediction, you use the test data. And then you already know the actual Y, right? Okay? Then you will get the error here. The error is from the test data X. Okay? And then F and alpha is from the calibration, the training. Right? And then you get the new output. Okay? And then you compare with this Y in here. That is in the test data. Is it clear or no? Can you get the idea? Can you open your camera so that we can communicate better? You don't talk and you don't show your camera, so I get confused when you only do a mimic. So what do you think? Do you understand the meaning of validation? Do you understand the meaning of training? Give me feedback. Amira, what is the meaning of training?
Like to force the data. Like to force the data, like to make it I cannot explain it, sir. Like of the data, maybe.
Training means you calibrate, okay? Training means you calibrate, you have your input, okay? And the output from the data to get the parameter. Do you remember last time you do regression?
Yes.
Yes. What do you get from the regression?
The R and R square.
The R and R square is the performance index of regression. That is the same as sensitivity, accuracy, and so on, right? So the actual things that you get is actually the slope and parameter, isn't it? That is,
Yeah.
I call as alpha here. Can you get it? The slope and parameter in your regression, okay, that is the parameter. Okay. So when you input your data into the model to get the parameter, okay, parameter is the slope and intercept, right? The slope and intercept in regression last time. That is this process, okay, to get the input, to get the parameter from the input and output, that is called training. Is that clear now?
Yes, clear, sir.
Okay, so when we say testing, what is the meaning of testing?
To test the parameter?
No, not just to test the parameter, okay? You have a new data set. Okay, when we say testing, that means you have a new data set. That new in here is not really new, okay? It's the same data that you already gather, but you separate, right? The whole data set you separate into two parts, okay? One is for training, the other one is for testing. Okay, so the one for training is to get the parameter, right? The one for testing is the one that you did not use for calibrating the model. That is the one that you use to test. How do you test? Okay, remember you have input with this X and you have output with this Y, right? When you say testing, you only input the X into the model that you have calibrated. You already have the regression model, for example, right? So in that case, you get the input X, you put it into the regression model that you have calibrated, and then you get the output. Okay, the output is the Y, okay, caret, which is the predicted based on the model. However, in your test data, you also have the Y based on the data, right? So then the Y that from the data compared to the Y from the model, okay, when you compare, okay, when you subtract one and the others, then you can get the, what is called error of the test. Do you get it? Okay, let me make it clearer. So you have your, can you see this whiteboard? Your training,
Yes.
okay, your training, and you have test data, okay? So in the training, you have X and Y. The same thing, yeah? You have X and Y. Basically, this is your whole data, okay? And then you divide into two parts, okay? So from here, you get the parameter alpha, yeah? You input into the model, you get parameter alpha. That is the meaning of training. So what is alpha? In your regression last time, this is the slope, okay, and intercept, okay? Now, when we say testing, right? So you also have the X and Y, but you don't use everything. You don't use the whole X and Y here. What you use is only the X, okay? You put it inside the model, which is your function, okay, to get the output. This output, I call this as estimate, okay, with the caret. But remember, in your data, you also have Y here. So then from this Y and this estimate, okay, you get what is called error. So this is called test error. So our goal is to make the test error as small as possible. I hope this is clear. Is there any question up to here? So let's come back to the slide. Okay, so holdout method, okay, we partition data into two parts, which is the training data set and the test data set. So how much is training data set? Can be 50-50, yeah, with the test, or 60-40 or 75-25. It's up to us, okay? And then what we will do, we will calibrate using the training data, and then we will test using the test data set. Okay, so of course the total data is just the training data set plus the test data set. Okay, so but holdout method of validation have certain limitation. Why? Because the training sample is not enough to produce good model. Okay, so if you put smaller training set, okay, you will get very large variance. So the model is not accurate. Now, if you put the training set is very large, okay, then your test set becomes small, right? In that case, your model, your testing is not reliable also, right? So how to overcome this problem? Okay, so to overcome this problem, we come up with the new method which is called cross-validation. This is the one that I asked you to do in WEKA last time, right? So how to do cross-validation, okay? So each record, okay, is used the same number of time for training and exactly one for testing. Okay, so how to do the cross-validation is as follow. Okay, first you divide the data into two equal size. Okay, the first data is for training set. The second is for testing. And then you swap and then you run again. Okay, so the total error is the summation for both run. Okay, so instead of two, now we have what is called k-fold cross validation, which is this is the one that you use. This is much better than just cross validation like this. Okay, why? Because in cross validation we define exactly two equal size. Okay, so in k-fold cross validation we don't divide by half-half. Okay, but we divide the data into k equal size. So what is k is up to us. For example, 5, 10. So what does it mean? It means your whole data set. So let me draw. And so suppose this is your whole data set, right? So you divide into, for example, 5. 1, 2, 3, 4, 5. Okay, so let's call this A, B, C, D, E. Right? So say K is equal 5 in this case. Yeah. So and then what you will do? The first 80% in this case, yeah, because K is equal 5. If K equal 10, then the first 90%. Yeah. So A, B, C, D is the one that you use for training. Okay, and then E is the one to use for testing. Okay, that is the first one. The second one, what you will do? Okay, the same thing, A, B, C, D. Okay, in the second one, you will do A is for testing. Okay, the third one, you will do B for test. Okay, the rest is for training. And then the fourth one, you will do C for testing. And then the fifth one, you will do D for testing. Yeah? The first one is E, right? So in that case, what you will do, you will repeat the procedure K times, okay, so that each partition is used for testing exactly once. So the total error is the sum up of the error for all the K runs. Is this clear? So tell me why this is better than whole out. Okay, so because when you use just whole out method, okay, say you only use the testing data once, right? So when you use k-fold validation, you basically use the whole data set for training and also for testing. So in this case, you minimize both bias and the variance. Okay. Now, you can also use another method which is called leave one out method. Okay. So the next one is, okay, k-fold validation is actually very good, right? Yes. Why? Because we use everything, okay, the whole data set as it is, okay? So for testing and for training. Oh, in that case, can we make it into extreme? Okay, instead of k equal to 5 or 10, can we just k equal n itself? Okay, so in that case, we have a new method which is called leave one out method. Okay, that means you will run k times, okay, and then you divide the data by k equal n, which is the whole data set. So what is the advantage? That means you utilize most data for training and effectively cover the entire data. Well, this is very good. Okay. The only problem with this method is computationally very expensive, yeah, because you will repeat to run n times, right? And then the variance is also tend to be very high because you only test one data. So in that case, we come back, okay? So the best validation method in this case is actually k-fold cross validation. That is the one that you use also last time in the practice of WEKA. So up to here, is there any question? So another method, okay, is called bootstrap. Okay, so what is bootstrap? So all earlier procedure, which is hold out method, cross validation, and so on, assume that the training record are sampled without replacement. That means no duplicate of the training and the test set, right? So there's another technique is called bootstrap. Okay, in bootstrap, the training record are sampled with replacement. That means each record is put back into the pool and still have equally likely chance to be chosen again. Okay, so there is a technique. This bootstrap have good things. Okay, so if the original data have n record, okay, then on average the bootstrap sample of size n would contain about 63.2% of the record of the original data. Okay, where it come from? Okay, so the probability of record chosen by the bootstrap sampling is based on this formula. Okay, 1 minus 1 over n exponent n. Okay, so when n is very large, okay, then the probability will approach this value, which is 0.63.2. Okay. So what is bootstrap anyway? So in bootstrap, the record are not included in the bootstrap sample will become part of the testing set. Okay. So the sampling procedure is repeated B times to generate B bootstrap sample. Okay, so the accuracy is something like this. So is there any question? So I already discussed with you several methods for validation. Okay, so if you forget everything else, so just remember that you can just use the k-fold cross validation, the one that you use in practice WEKA last time. Is there any question? Okay, so if not, I will continue with the next slide. Can you open in Lentera about classification, discriminant analysis? So I will close the model assessment. Okay. So this is basically for AI. Okay. So actually, you're supposed to understood basic probability and Bayes theorem in this slide. Have you learned statistics before? Yes or no? Have you heard about Bayes theorem?
I guess we got it in business statistics.
Okay, so you already learned that. That's very good. Okay, so in this slide, I will discuss mainly about what is classification, and then we touch a little bit about linear discriminant analysis. Okay, so for the practice, you can use WEKA later. Huh? So let's see with this problem first. I have two classes. Okay, for each class, we have two variables on the left bar and the right bar. Can you see that? So this is class A and this is class B. Okay. For each class, there are two data, two variables. This is left bar and right bar. Okay. So the question is, okay, given this example of class A and given this example of class B, okay, my question to you, what is this class? And what is this class? A or B? What do you think? I give you example. This is class A, this is class B. Okay. So each class have a left bar and right bar. So what is this? Can you see the pattern? Hello? Are you
class.
eh?
Class.
This is class B. Why? Why this is class B?
Because the left one is bigger than the right one. And in class B, all
Wow.
of them right there.
Yeah, very good. So you are basing on the pattern, right? This is the left one is larger than the right one. And you can see the class B is actually like that. How about this one? At the bottom here. A or B? What do you,
If we look at the pattern of class A.
yes, this is the pattern of class A. Very good. So, okay, said, okay, this is B. Okay, what is the rule? Okay, the left bar is smaller than the right bar. It is an A, otherwise B, isn't it? So, based on this example, you create the rule, right? Based on this rule, you predict the new instant which is not in your data, right? Okay, let's practice again. How about this one? Oh, this is harder. This is class A and this is class B. So how about this one? This is A or B? On the top is A or B. Given this sample, okay, what do you think? Eunice.
I guess the top one is B. Oh, sorry, Yun.
Ah, the top one is? The top one is B. How about bottom? How about this one?
A, sir.
Why?
Because the pattern is the same.
Oh, because left and right is the same. Okay, so you created a pattern, okay? You created a rule based on the pattern that you get from the example, right? So the rule is if the two bars are equal size, then it is A, otherwise it's B, right? So then this is A. Okay, How about this one? Wow. How do you make the pattern now? So what is this? This is really hard. Okay, what is this? This is A or B? Hmm? So, anyone? What do you think? So this is A or B? Are you still there? Josephine, what do you think?
I think it's B, sir.
Why? Why this is B?
The A numbers is too low.
A number is too low, but this is 6. You also have 6 here.
Yes, sir. I don't know.
Eh?
That's
So what is the rule then? Someone is using the same account. Still Zoom. Anyway. Can you see this? So okay, this is B. Okay, the rule is as follows. So if the square of the sum, okay, of the two bars is less than or equal to 100, then it is A. Otherwise, it's B. Okay, so you may wonder why did we spend so much time with this game? Okay, suppose we wanted to show that almost all the classification problems, okay, have also geometric representation. Yeah. So look at this, okay? This is the first problem that we discuss about, okay? So when you see, if you plot this left bar and right bar, okay, here is the rule again. So if the left bar is smaller than the right bar, it is A, otherwise B. Can you see? Okay, so this is the left bar and this is the right bar. This is class A and class B. Okay, so in problem 2, okay, A and B is something like this. So if the two bars are equal size, then it is A. Okay? Otherwise, it's B. So, okay. Now, in problems, the third problem is something like this. Okay, if the square of the sum of the two bars is less than or equal to 100, then it is A. Otherwise, it's B. So, what is this about? Classification. Okay, so it's something like this example. And you see, these are the collection of data. For example, we have two insects, yeah? Katydids and grasshopper, right? So now I have a new instance of this insect here. The question, given this example of katydid and grasshopper, what is this? This is katydid or grasshopper? What do you think? Huh?
based on the body size.
Based,
Its body size.
based on the body size, what is that?
Don't really know, like for example, the length of its thorax. I don't know.
Hmm?
The length of its thorax. I don't know.
Yes. So what you just did is very excellent, Shane. Okay. So you are mentioning about the feature, right? The body size, the thorax, and so on. So these are the feature. Okay. So any domain of interest, we can measure some feature, okay, some variables, right? For example, maybe the color, maybe the wings, maybe the thorax, maybe the abdomen length, maybe the antenna length, maybe the leg length, and so on. Yeah? So all these features is the variable that actually you measure. Okay? Based on the measurement of those variables, then you can have data, right? So example here, we only use two features, which is the abdomen length and the antenna length. Okay, so these are in the measurement. And then this is the class, right? Either katydid or grasshopper, right? So the classification problem is something like this, okay? Given this training database, okay, you want to predict the class label of what? Of previously unseen data. So say I have the same measurement here, okay, number 11, okay. Abdomen length is 5.1 and then antenna length is 7. What is the class? Okay, so in that case, what you will do? You will plot, right? Antenna length, abdomen length, okay, something like this. And then what you will do? You plot, of course, if you have a lot of samples, so you can see clearly, okay, this is the katydid and this is the grasshopper, okay. So then you can put your previously unseen instant is in here, okay. Then you will say, what is this? What do you think? Is it katydid or grasshopper based on this measurement? Anyone? Are you still sleepy? Can you open your camera, please?
It's katydid, sir.
Huh? Why? Why this is katydid?
Because it is closely.
Because this is closer to this group of katydids, right?
Yes.
Okay. So how do you say that this is actually katydid? Because this is closer. So one way is to create a line here, okay, to separate the two of them. Hey, this line is not regression line. This is classification line, right? So if the previously unseen instant is above the line, then it is katydid, okay? Or else this is grasshopper, right? So this is a linear classification based on a simple line, right? So if we have not just two variables, but three variables, right? So the point will be in 3 dimensions like this, right? So, and then we have a katydid and grasshopper, we put it this way. And that line is no longer a line, yeah, but a plane, right? So if you have more than 3, okay, that line is no longer plane, but a hyperplane. Okay, so if you are interested in lower dimension, so then you, what you will do is to project all this data into this dimension, okay, in the bottom here. Then you will see that actually the plane earlier is no longer plane, but actually a curve. Yeah, can be quadratic, can be cubic, and so on. Okay, So if the linear in higher dimension does not mean in linear in the lower dimension. Okay. So this is the example of application of this classification. Okay. For example, you want to do credit rating. Okay. Whether this person is defaulted or not. Okay. So you want to check based on your data whether this is a virus or not. Okay. Whether this student will be pass or minor or fail the exam, for example, or personality of sociables of certain people, whether it is a noise or the sound, and other things. Yeah. Classification basically like this. Okay, you have class of data, nominal data or ordinal data. So your dependent variables are classes. Okay, say for example, very satisfied up to not satisfied. Okay. So these are the application of classification. Okay. Based on this, you can see, again, you have X and Y data, right? The same as regression last time. So you have X and Y. In regression, the Y here is quantitative. Yeah? In classification, the Y, okay, the output is classes, nominal, categorical data, ordinal data. That's the difference. Both of them, if you have the X and Y, this is called supervised learning. So my question, can you think of other application? Say in your group project, can you use some of your variables as classes that you want to predict? Is there any application that you want to use? What do you think? Anyone want to say something? Okay, so as long as you can create a categorical data, okay, for your dependent variables, so these are example again, okay, so whether email is spam or not, right? Personality classification is introvert, extrovert, intuitive, or feeling. Yeah? So say your market segmentation, okay? Whether they are psychopath or normal people or melancholy. Okay? In the stock market, you want to classify whether they need to buy or to sell or to keep the stock. Okay? In the supermarket, for example, you want to keep low discount, medium discount, or high discount, and so on. Right? So these are example of application of classification. Okay. So now in the previous example, we used bar chart problem, right? So which of the bar chart problem can be solved using simple linear classifier? Okay. So the first problem earlier, we can see that we can perfectly, okay, separate the data. So this is linearly separable. So this is perfect. Okay? If your problem is something like this, and you use a linear model, it is supposed to be quadratic, but you use linear model. So it's still pretty good. Okay? You have some misclassification here and some misclassification here. Okay? But if your model is something like this, quadratic, right? So if you use linearly separable, then this is pretty useless model. Okay? Because you cannot separate that. Okay? You cannot separate the classes. So not all model can be used for certain type of data. Yeah? So you need to try, okay, which model is used for different type of data. You got it? So, and then from there you can get the accuracy and the confusion matrix. Yeah? So accuracy is basically just the number of correct classification divided by the total data. Okay. So, and if you look at the accuracy is just a single number, right? So better looking is actually the confusion matrix. Okay. The true value is in the diagonal. Okay. And these are the error. Okay. That will produce certain additional useful information for you. Okay. So one method to classify, okay, is to use simple linear classifier. Yeah? So this is called supervised learning. Okay. Our goal is to classify the object. So the object can be people, can be customer, things, and so on, into one of two or more groups. Okay, based on the set of feature described by the object. Okay, so we assign the object to one of the number predetermined group based on the observation made on the object. Okay, so in LDA, or a linear discriminant analysis, our goal is to minimize the total error of classification. So to do this, we use what is called Bayes rule. Okay, so suppose you have G groups or classes. Okay, the Bayes rule is to assign the object to group I, okay, based on the conditional probability like this. So if the Pi given X is larger than Pj given X, X is the feature of the data that you have. I and J are the groups. So that means given the data, okay, if the probability of that data is to the I, group I, is larger than all other group, okay, then use that group I as the classification. Okay, so this is just review of probability. So since you have learned about it, so I just skip this review. Okay, so conditional probability. Conditional probability of an event, okay, depends on the occurrence or non-occurrence of other event. So we use PA given B, something like this. Okay, so we say that the probability of A will happen given that B already has, or this is the probability of A among B, right? So basically, is the joint probability divided by the marginal probability of B. Okay, so PA given B is just the joint probability divided by the probability of B itself, the marginal probability. Yeah? So the same thing here. What we want is to get this, right? Given the set of measurement X, we want to find the probability that the object belong to group I. Okay, but in practice, very difficult to get this. Okay, it's easier to get the reverse. Okay, what is this? I know the group, and then I will measure that. So if I know this group, say candidate or grasshopper, for example, okay, I and J is the candidates or grasshopper, and then I will measure all the measurement of candidate and the grasshopper, right? So given the I, the group, I can measure. So the probability of getting particular set of measurement given that the object comes from group I, this is easier to get. right? So, but we can solve that problem using what is called Bayes theorem. Okay, so this is what we know, right? And this is the probability of group I. Then using Bayes theorem, this is the formula of Bayes theorem, we can find the other way around. Okay, so this is what we get. So this probability is called posterior and this probability is called prior. Okay, so the marginal probability is called prior. Okay, and this is for all other groups, okay, that we have. So prior probability, PI, is the probability about the group I without making any measurement. So in practice, we can assume the prior probability equal to all groups or based on the number of sample in each group. Okay. While the posterior is for each measurement value, we need to get the relative frequency for each group. For example, okay, so if X is 1, 2, 3, 4 until 5, and X is 1, right? Then to get the P of group 1, we need to form the frequency distribution or the histogram of group 1. Okay. Similarly, for X equal 1, group 2, and so on. So we need to get the frequency distribution for each of these. So if the measurement have so many values, so we need a lot of sample of data to fill all the frequency distribution for each value and each group. So in practice, this will require a lot of data. Okay? So sometimes it's impractical to do that. Okay? Except for few value or few groups. So a technique to solve that problem is to assume. Okay? We assume normal distribution. Okay? So this is the multivariate normal distribution formula. Okay? So this is the covariance matrix. Mu is the mean vector. Okay? X is your data. So based on this, okay, linear discriminant analysis can be derived. Okay, so the derivation you can check in my website. Okay, but the result is something like this. So you assign, okay, object K to group I that has maximum value of Fi. So Fi is computed using this formula. Okay, this formula comes from the multivariate normal distribution. Okay. So let me give example. Say factory ABC produce very expensive high quality chip rings that their quality are measured in terms of curvature and diameter. Okay. So this is the curvature and this is the diameter. And then the result of the quality control expert is something like this. Okay, this is pass and not pass. Okay, so you have two classes, right? Pass and not pass. So now as a consultant to that factory, you get a task to set up the criteria for automatic quality control. Okay, so the manager of the factory also want to test your criteria upon the new type of chip rings that even human experts are argue to each other. Okay, the new chip ring have curvature of 2.81 and then diameter of 5.46. Okay, can you solve this using LTA? Okay, so you plot the X and Y. What is the X and Y? The curvature and the diameter. Okay, this is the X and Y. We put these two and then we plot. And then the triangle here is the new data set unseen. Yeah? So our goal is to find the line, okay, that maximize the distance between group and to minimize distance within group. So what you will do is to separate the data. Yeah? The X is the feature or independent variable of all data. Okay? Each row represents one object, and then each column represents one feature, which is the curvature and the diameter a while ago. And then the Y is the dependent variable, is the group, the class. So because it's class, so you can put any value, yeah? 0 and 1 or 1 and 2, 2 and 3 is up to you. Okay, so in this case, I use 1 and 2. Right? So, and then what we will do is to separate the X into several groups. Okay, so because you have the first group is 4, the second group is 3 data, right? So then we separate them into 4 and 3. Okay, so we call this X1 and we call this X2. Okay, and then we measure the mu which is the mean for each group. Okay, so this is the mu1 for each group 1, and then this is mu2 for the from here. Yeah, this is the average of each feature here. And then, of course, you can calculate the whole mean for the whole thing. So this is the global mean feature. Okay. From there, we center the data. Yeah. So we center the entire data to the global mean feature. Okay. We separate them up also for each group. Okay. From there, we can calculate the covariance matrix. Yeah. We already practiced last time, right? The covariance matrix. Yeah? So those are the foundation. So from that, we have C1, which is the covariance matrix of group 1. Okay? C2 is the covariance matrix of group 2. Okay? You have practiced last time. So from there, we can calculate what is called pool within group covariance matrix. What is this? This is the combined. Yeah? This is the combined covariance matrix from the two groups. Okay, so we combine these two. So we have a new covariance matrix based on the number of data for each group, okay, N, I. And in here is the total number of data, which is 7, right? And then CIRS is the covariance matrix for each group I. Okay. After that, what you will do is to inverse that covariance matrix, yeah? And then put it into the formula later. Yeah? The prior probability is just the number of data on each group divided by the total number of data. You have 4 and 3, so total data is 7, so you get the prior probability like this. Okay, and then all of that we just plug into the formula. Okay, plug into the formula. We have the inverse of covariance matrix. We have the mu I, which is for each group, right? And then we transpose this, and then again, we have the inverse of covariance matrix. We get the Fi. Okay. So based on the Fi, okay, for example here, okay, so this is the mean corrected data. This is the Fi, F1 and F2, right? So if the F1 is larger than F2, so the classification is 1. Yeah. If F2 is larger than F1, so the classification is 2. Like that. You see? Okay. So then if you have a new data set here, okay, 2.81 and 5.47, right? So you compute again, and then you calculate the F1 and F2. Whoa, you see very close to each other, but F1 is still larger than F2. So, no, F2 is larger than F1. You see, 85, this is 49. So the classification is 2. So with this, you can predict, okay, the classification based on F1 and F2. Yeah. Is this clear until here? So LDA, that is in principle, okay, you compute this score value with this F1 and F2, okay, based on the technique that we discussed a while ago. Okay, so in summary, so you will see that classification is just a technique to find the relationship between one categorical dependent variable, okay, the output, and the set of independent variable of any type. Okay? The dependent variable is important, must be categorical. Okay? When you use LDA, okay, this is one of the technique of classification, then you have certain assumption. Yeah? If you deal with the model, what you need to do is to understand what is the assumption. Yeah? LDA have three assumptions. Number one, the data is independent, has independent multivariate normal distribution, and the data must be linearly separable. And then, if you look at this a while ago, each group of data has equal covariance matrix. Yeah. So, and be careful. Okay. This coefficient of discriminant function F1 and F2 has very different meaning from the regression. Yeah. This is to classify. This is to separate, to discriminate. Yeah. To discriminate. Okay. Not to regress. Okay, up to here, is there any question? So if not, you can take rest for 10 minutes. So now is 10:18. Come back again at 10:28. Okay.
Okay, sir.
Yeah, go ahead.
Wait, let me share my screen.
You want to ask about WEKA? Go.
Do you see my screen, sir?
Yeah, I can see your screen. Okay.
Oh, okay.
Or
So,
correctly classified is only 61%. Okay.
oh no, this is from the CSP, sir. What I want to try is from the IRFF, but the
Okay.
problem is that I couldn't open the file, sir.
You cannot.
Wait, let me show you. Yes, sir.
Okay, this is not okay. Can you open the file in text file first so that we can?
Right.
Okay,
Oh, yeah. Let me scroll.
is this the one?
Yes, sir. This is the one.
Okay, let me check. Okay, so that is the problem here. Can you see? You use semicolon instead of comma.
Oh, here, this one, sir.
No. Let me here in your data. You must use comma instead of semicolon.
Oh, and what if I switch out to this one, sir?
So you can search and replace, or semicolon you replace with comma.
How about the comma replace the semicolon?
No, you cannot. You cannot.
Yeah, okay.
So
Okay,
you
then.
just do in here edit, okay, and then
Yes, it's fine, but sir.
replace, okay, and then semicolon. You type semicolon there, okay, and replace with comma.
Yes.
Case,
All right, yes, sir.
much case, much case, and then you find next. Is that correct? Okay, replace. Okay, then it's correct.
Because
So you can replace all, yeah. Okay, so cancel.
right, sir.
Is that correct? So save it now. Okay, now you can try again.
Still, sir.
A problem? Oh, relation expected. Oh, where is the relation expected? Oh, there is some problem with your first line probably.
The first line is this one, sir. But I couldn't find the error.
Wait, I will check WEKA, right? relation,
Yes.
and then where is your at relation correct? Attribute. Okay, so attribute is time. Is this correct? The category that you have.
Yes, sir.
Okay, so all of this correct.
Yes. I already checked it, and it's all correct, sir.
All correct. Okay, so what is the error a while ago?
It's on the first line.
Line
Line one.
one. Line one. So at relation expected.
Oh, sorry.
Okay. Those three. Okay, maybe you did not save, or maybe you download in different place. Is it?
And I already saved it, sir. But let me close it again.
Okay.
All right.
Did oh
What's this?
WEKA File Manager, you have installed so many scheme tool. Okay, later you can
Uh,
which data that you use. Okay.
Still the same, sir.
Maybe in your data, can you delete the whole line of first line? I think there is certain ASCII character that you cannot see.
All right. Not this one.
Okay, can you open that again? So
Oh, yes.
where is your earlier data? That one.
Not that one.
Okay, open it in text file. Say, so the first line here, you delete everything, okay, and then you do it again. Delete everything, okay. Then, okay, good. Okay, so save it.
Let me try again.
Uh-uh.
Still the same, sir.
You still have this, before the relation, it seems you have certain character. This one, can you see the character there?
Yes, sir.
So you probably want to delete the whole things here, okay? I'm just guessing there is certain things that in your file apparently. Delete again. Okay. And you say,
Then,
and then now you create again at relation. Food. Okay. Save. Supposed to be okay, right?
still the same, sir.
Still has.
Yes.
Oh, that's super strange now. Keyword relation expected, but they read this. Do you want to try to open it in other text file, text editor? Maybe you can see. You cannot see that in this editor, but you can probably see it in other editor. Do you have any other editor aside from Notepad?
I already did the previous one that I have, sir. I still need to download it again.
Oh, say for example, you can download the what is this called? Sublime text, for example, and then you check there. I think there is some ASCII character in the first line.
Okay, sir. Then let me download it first, and I will chat you after
Yeah,
class,
okay.
sir.
Yes, okay.
Okay, thanks, sir.
Okay. Yeah, thank you. So let's come back to the class. Hello, everyone. Okay, so let me share my screen with you. So if you want to do LTA, right? So, here, this is my WEKA. So I will close my MATLAB. Okay, so this is my WEKA. If you want to use LTA earlier that we discussed, okay, you go to Packet Manager. Can you see? So, and then you can check, refresh the case. Of course, you need in my case, I already installed, so I put it in install. You can check all and you can search, okay? So you just install this packet, discriminant analysis. So this is the Fisher linear discriminant analysis, okay? And this is LTA and QTA. So once you have this, you can use the LTA in WEKA, okay? In fact, you can also install many others, yeah? So in my case, I install, for example, scan distance, tabu, time series, wavelet, and so on, yeah? Including Excel and Python connector, yeah? So it's up to you to install all other packets. Yeah? WEKA is community based, so you can install many other packets that is already available in public. Yeah? You can check on your own. Yeah? Okay. So once you install that, then you can start to use WEKA. Okay. So is there any question so far? So let's discuss something else. Yeah? So we have, when you practice WEKA last time, okay, probably the easier way to interpret the classification is using decision tree, right? So that's what we will discuss today, okay? Decision tree. Okay, here it is. Okay, let me go. So this slide is also in Lentera, so you can also follow from there, okay? So we already discussed what is classification, right? So given the collection of record, which is the training set, okay, its record contain of set of attribute, the variables, and then one attribute, the last one usually, is the class, right? So we want to find a model for that class attribute as a function of the value of other attribute. Yeah? Our goal in classification is to, okay, determine the class of previously unseen record. Yeah? So you will assign this previously unseen record to a class, okay, as accurately as possible. And decision tree is very good for this. Yeah? So the test set, so we have training set, we also have test set. So the test set is used to determine the accuracy of the model. Yeah? So usually the given data set is divided into training set and test set, okay, using k-fold validation, and then we validate them. Okay. So these are example of classification tasks. Again, I would like to highlight that, for example, predicting tumor either as benign or malignant, okay, classifying the credit card transaction as legitimate or fraudulent, okay, and categorizing the news story as finance, weather, entertainment, sport, and so on. So these are example of classification tasks. Because of this method, we have what is called machine learning, basically classification tasks. So we have a lot of things in AI. Yeah? So there are many classification techniques. Okay, so rule-based, okay, memory-based, neural network, naive-based, and so on. So discriminant analysis we already discussed. So if this is the class of AI, usually I discuss one by one, but this is in big data, so I just discuss in brief today only discriminant analysis and decision tree. Probably next meeting we discuss about neural network. Yeah? So the others I will just skip so you can read on your own. Okay, so so this is your data set. Okay, the whole data set you divide into two parts. Okay, this is the training data set and then the test set. Okay, so in the training data set you put into a learning algorithm. Say for example decision tree. Okay, it will learn the model. Okay, and then you will create the model. Then you apply. That is to predict. Yeah? When you apply, you use the test set. Yeah? To predict. You don't use the training set, but you use the test set to predict. Okay. So what is decision tree? Decision tree is a hierarchical tree structure that used to classify classes based on the series of questions or rules, okay, about the attribute of the class. So each record attribute, each row of your table, yeah, okay, consists of X and Y. Okay, X is the attribute, Y is the classes. Yeah. So the X is any type. It can be binary, can be categorical, can be rank, can be quantitative, and so on. But the Y is important here. Yeah? The Y must be class, so it must be binary, nominal, or ordinal only. So what is the output of this decision tree? Is a rule. Okay, is a tree rule. Example of tree rule is something like this. So if the percentage is larger than 90, yes, so the grade is A. If no, okay, is it the percentage is between 80 to 89, yes, grade is B. Yeah? If no, if the percentage is between 70 to 79, yes, the grade is C, and so. Okay, so these are example of rules, decision tree rules, to specify the grade, right? So the nice thing about decision tree is, given the data set, okay, you only fit the data into the model. Say for example, the model, in this case the software is WEKA, okay, and you use decision tree. Okay. So you only need to give the training data, okay. Say in this case can be categorical or continuous. Okay. In this example, the class is only binary. Okay. Then WEKA will create this decision tree. Okay. This is example of decision tree that created by WEKA based on this data. Yeah. So it will ask refund yes or no. So this one, yeah, refund yes or no. If no, then will not cheat. Okay. If yes, refund last year, right? That means will not cheat. No. Okay. So, and then here is the splitting attribute. Okay, refund, okay, marital status, tax income, and so on, taxable income, and so on. These are the splitting attribute. Okay, so now if the marital status is either single or divorced, okay, asking again about the tax income. If the marital status is married, again the cheating is no. So this blue is represent the class. Yeah? The cheating is no. Okay, so using this decision tree, okay, you can represent the whole table. Okay, another example. Okay, look, I can also use different decision tree here, right? So that means you can have more than one tree to fit the same data. Okay, so depending on how you model the decision That's why you can see even in WEKA there are many methods to do decision tree, right? So different method to do decision tree, you will eventually create a tree. Okay. So now if you want to apply the model or to test the data, okay, say for example, I have a new data set unseen, okay, no refund, marital status is married, taxable income is 80, right? Whether it will cheat or not in the tax. So you start from the root 3, you check refund or no, so no, then the result is check the second one, yeah. Then marital status yes or no, yes. So the result is no, that means it will not cheat. Yeah? Right? So assign the cheat to no based on this decision tree. You see it? So this is another example of playing tennis or not. Okay, so these are the data that we have. And then this is the decision tree that created. Yeah? So outlook, okay, sunny or overcast or rain. If sunny, check again the humidity, okay, high or normal. Yeah? So N in here mean the class, mean no, don't play tennis. P here is play tennis. So based on that rule a while ago here, okay, you can actually also represent that rule into a logic. Yeah? So these are the logic. If the outlook is sunny and the humidity is normal, right? Okay. Or if the outlook is overcast, or the outlook is raining and the wind is weak, okay, so then you should play tennis. So play tennis based on all the rule of P. So you can create a rule, okay, logical rule based on the decision tree. Okay, very nice. Okay, so okay, open the WEKA Explorer, okay, and then there is already file there in WEKA, okay, weather nominal.arff, and then try to classify, okay. Okay, so can you do this? Now you practice. So in my screen, so I open my WEKA. Right, so I open WEKA Explorer. And then you open the file. So that is in C, in program file, right? In my case, in WEKA, I put it in program file, and then go to data. There, weather nominal ARFF. So I don't know where you put your WEKA. So inside the WEKA folder, have data folder, and then these are the example of data that already included, yeah, inside the WEKA. So you can put this, use the weather nominal ARFF there. Okay, there is 14 instances, that means 14 rows, and these are the variables, yeah, outlook, temperature, humidity, windy, and play. Okay, after that, what you will do, you classify, right? Choose the model. So we use 3. Okay, so say I use J48. Okay, so I use cross validation 10, and I do. Okay, this is the nominal. The Y, the dependent variable, is play. So I put start. So I get this result. Oh, only 50%. Wow, not that good, right? What is the tree here? This is the tree. Yeah. So if you use the whole training set, okay, instead of 10-fold validation, you will see I get 100%. Can you see? But if I use K-fold validation, okay, a while ago, so I get only 50%. So this is the difference. Yeah. If you use the whole data, okay, as your training set without cross validation, you get very good result, right? This one, so 100%. But this is dangerous, yeah, because this is tend to be overfit, right? So, but once you use K cross validation, okay, you get only 50%. So the question is now, okay, I use this, can I resample so that I can improve? Okay. Okay. Alternatively, you're supposed to be able to use decision tree. Oh, ID tree is no longer here. Okay, so you can use random tree. Okay, and start. Oh, again, I got only improved little bit, yeah. From 50%, I got only 57%. Okay, so your practice to improve this. How to improve that one. And then once you finish, you share your screen, yeah.
Well, I download it.
So,
It's not included.
it must be included. So where is your WEKA folder?
Oh, okay, wait. I should
You want to share
try.
your screen, yeah. If you share your screen, I can probably help you.
Wait, sir. I need to find my WEKA folder first.
Okay. When you install, where do you put your WEKA folder? Maybe in download?
Okay.
How about the others? Can you find your data? Or do you have the same problem as Amira?
Cannot, sir.
You want to share your screen so that I can help you?
I don't have the data, weather data.
Yeah, exactly. So the data is there already in WEKA folder. Where do you put your WEKA folder?
Oh, download.
In download, okay. Can you open?
Wait, I don't know.
You share your screen so that I can help you. Anyone want to volunteer to share the screen? Okay. So no, the whole screen so that we can see. Oh, where is your data? Where is your WEKA? Where do you install it? Can you go to C? You go to Explorer, File Explorer. Okay, you go to File Explorer and then search WEKA so that you will know where do you install your WEKA. Is it in program file? Anyone want to share screen so that I can help?
I'll share the whole screen, yes, sir.
Yes. Okay, so this is not the WEKA itself, right? So can you go to, oh, you're using Mac. So there, this is your WEKA, right? So there, WEKA file. Can you put in WEKA? Can you see the WEKA? Is this your WEKA file? Is your file?
What, sir?
This one.
Oh,
So what is inside here?
which one?
Yeah, that one.
Oh, nothing.
Nothing. How about the other one?
Mine also like that, sir. Nothing.
Nothing. That's the package only. The native also nothing.
Only this one.
Okay, so can you open your WEKA in that case?
This one. This is WEKA.
Yes, okay. So open file. There, it, oh,
Download.
what is inside supervised? Is this your own file or? Oh, that is your own file. Okay, can you search in Google, because you are using Mac, right? So can you search in Google, where is the WEKA data in Mac?
Okay.
Okay, so I think data in Mac. Okay. Oh, there.
Oh, this one.
So once you install, right, where's the data? Does it say? Where is the installation? Down, probably. Oh, did not tell. So can you go before this? How to open WEKA in Mac? What is this? Can you click this triangle? Okay. Does it say? Browse down. Okay, so did not tell. Okay, let me check. Let me search. WEKA data in Mac. WEKA data in Mac supposed to be. So what is the name of the data a while ago? Nominal. Oh, weather nominal ARRF in Mac. Can you search in Google WEKA ARRF in Mac? Oh, there, WEKA data set. Okay, so if you don't have it, you can download directly from this website. Also, you can also do this. Let me share my screen. There. So I will put in the chat. Okay. So you can download from this weather nominal ARFF. Okay. Does it solve your problem? Anyone want to share screen? That you already doing it? Can you compare J48 and ID3? Can you also compare just training all data set and K fold validation? What's the difficulty? Can you share? Eunice, what happened?
I don't understand.
You cannot understand?
What if after I got the after
After you got the data,
and it's still in the browser, not yet in my
really?
file.
Really?
Like this browser. Still like this.
Yeah, yeah. So what you will do with that?
Put it in the WEKA.
No, you just copy that one.
Oh, copy.
And then put in the text file.
The text file.
Yeah, just copy and then put in the text file. You just
Where is text file?
any text file. You can open any text editor.
Oh, this one.
Yes. Copy, paste. Okay, and then save it in your folder, your own folder. In supervise, right?
In supervise.
Where do you put your data?
Oh, I forgot. I think in download. I put it in download first here. What is the file name?
You check your Explorer. So where do you put your and
This one, download.
okay, so you go to there in supervise. You put it in supervise, right? And,
Okay.
hey, the format. What is the format? ARFF dot ARFF. Hmm? How do you make last time?
Oh, convert it into ARF.
Yes. Last time.
I think last time I used directly from WEKA.
Okay, so you can also use directly from
I forgot how.
Okay, just put it as text file in that case. Save as text file.
Yeah, already, right?
Okay, so can you Do you think you can open it in WEKA? You can try. The file type.
Oh, text.
There is no text.
No.
Exactly. So can you do? Can you change it to ARFF?
I don't know how. I
Okay,
forgot.
again in your data a while ago. Okay, here, can you save as?
Wait, no. I think last time I can, but in WEKA, but I forgot.
Okay.
Oh yeah. How to get out from here, sir?
Huh?
To go to the first page of WEKA.
Maybe in the menu on the top, and then you can just close it. Exit. Yeah.
Oh, this one.
Okay.
I forgot, sir.
You forgot.
Wait, I open internet.
So, do you remember how you make the ARFF last time?
Yeah, I forgot.
Okay. So as long as you can just put you can save as text, okay, the ASCII text, and then you just rename it as .arff, then it will work.
Okay. Kok ini text ya?
No, the file that you copy a while ago.
Oh, the weather one.
Yes.
Yeah.
That one is in RTF, right? That is the problem. So RTF is rich text format. So the format is the problem here. So you need to change the format.
The format of what?
This file that you just saved. The one that you save, this one is RTF. Can you see that?
Yes.
In rich text format. Okay, so you are saving it in the wrong extension. Okay, so the question is, can you save as this to other?
Cannot. No, there is no option.
There is no option to rename, for example.
Oh, rename can only rename
Only rename
the file.
cannot change the format.
Yeah.
Okay, so in that case, if you open a new one, if you copy that and then you create new, say you copy everything and then you create a new text file, can you change the format?
And copy it to where?
Say you create a new text file.
Oh, new text.
And then is
Open
there
in.
any possibility to save as this one? Okay,
Oh, this one, yeah.
format, there is no other way, right? Okay, so in that case, you cannot use this text edit. So you need to download another software to save as. So I suggest you download Sublime Text.
Okay.
Can you?
Download what? Sublime text.
Yeah, search in Google Sublime Text format. There, sublime text. There.
You can, sorry, sir.
Sorry, Amira, you want to say something? Probably you are experienced in.
Maybe I can help you in this. You can
Okay.
directly rename it. You can go back to your file better. Yes, and then you add rename.
And
No,
then
no, no.
rename.
Oh, wait. In delete first, yeah. In rename this.
And then
And then directly add .arff.
can.
Add.
No, no, no.
No, no.
Weather
Weather dot
.arff.
arff.
Oh,
And then you can directly open it from the WEKA.
Okay, try.
okay. Where is WEKA?
Let's try. So I'm not using Mac, so I don't know.
Where ya tadi?
Where do you put your data? Oh, in download, right?
Oh. Hah,
No, not in desktop. In download.
why not? Why there is no download? Oh, ini loh. No, no.
No, where did you put your?
In my desktop. Yeah.
Okay, so try to open that better.
In my, yeah.
In your desktop, there is. In supervise, this one. Folder is supervise. Where did you put the supervise?
Document. Oh, document.
Man,
Haha. Loh.
there. ARFF, not GZ. ARFF. There. You did not. The one that you saved a while ago, ask where did it goes. Or maybe this one did not change yet. So can you change the weather dot ARFF? Rename. Dot ARFF. Enter. There. Okay. Okay. So open that with WEKA. Supervise. Not there. Oh, where did you save that a while ago?
In supervise.
Supervise. But why is not there? With supervise. Maybe you need to refresh.
Sir, hello. Maybe you can try on WEKA directly, rename it.
Oh, try.
You open in CSV first, this document, and then you open first.
Huh?
And then
And in WEKA.
Oh, in WEKA.
Yes. No, yeah, that file. Open. Then you change the files of type
Oh,
into CSV. Yes. And
okay.
then, why it didn't show up there?
because she renamed it to ARFF already. Is that correct? ARFF?
Yes.
ARFF, yes. It's not there.
How about all files, all files?
All file. Oh,
Ooh.
there. Oh, the name is not that. ARFF. Okay, then open.
Oh, there is nothing.
There's nothing. All file.
Why why the extension is RTF?
Yeah, the extension is not ARFF.
Yes.
That's why cannot open. Oh, try to use converter. Oh. Just click OK, try. No, cannot. Again, you can try. You open a new file. Okay, you copy that. You open that. You save into a new file. Okay, weather.arff, not RTF. That one you copy everything, right? And then
New.
new. Okay, paste and then save as that one. There is no way to save as a text file.
No.
Oh, that's so bad.
Yes.
So in that case, I suggest you really need to download the Sublime Text.
Okay, okay.
Okay. Try.
Oh, download.
Yeah, download is download that one. So for Mac, right? Is there any for Macs? There. Mac,
Huh?
Mac OS on the top.
Oh, this one.
Oh, yes. Okay. So can you install that? Okay, there. So you open the Sublime Text. Open. Okay, so copy.
Oh no.
Actually, no need to.
Oh, no need. Okay, cancel.
Okay, so you just there, and then you save as now. File, save as. There, you just save as in where? In document.
Document.
And then
Oh,
inside document have supervise, right? So
yes.
inside supervise there, and
Save.
no, you name it. Oh, there, name it weather.arff. .arff. Okay, save. Okay, finish. So now you can open using your WEKA.
Oh, this one, yeah.
Yes.
Oh,
Yeah.
yeah.
Okay. So then classify. Go to classify.
Oh, classify. Okay.
Okay, and then choose. On
Choose. Oh,
three trees on that triangle down there.
eh. No. Oh.
Choose the triangle first. Now J48. J48.
What, sir?
J48.
Oh, J48.
Okay, so
Start.
there you got it.
50.
This is only 50%. Can you improve?
Don't know.
Don't know. Okay, go back to your WEKA,
Which one?
not
Prepare.
the Explorer. No, the WEKA, not this one, the WEKA. The WEKA itself.
How to?
Okay, you close this one so that you can see. Okay, no. think you need to close this one also. Close that one. There, okay. So tools, packet manager, okay. Now search in the search packet search, you type, what is that? Simple educational learning scheme.
Simple.
Simple educational learning scheme. So I will put in the chat. There. Without space. Learning scheme. Or simple educational is fine.
Oh, wait. Like this.
Yes, search. Click.
Clear.
Huh?
Search or clear?
Search.
Huh? Where is search?
Just press enter. There. You get the simple educational learning scheme there. Can you see? Click that and then install. No, not the assembly. The second one. There. Install. Install.
This one, yeah. Install.
Button. No, the install button. Let me annotate. Here.
Oh.
There. Click yes. Yes. Okay. Now you install a new package. Okay, install successfully. So you go back to, you can close this. Okay. Go back, close this one. Now you can go to Explorer again. And then open your file a while ago. No, is that in document? Supervised lab?
You say.
Better, okay. Now classify. Choose trees. Now you have ID 3.
Oh.
Right. Oh, you can now. Right. So this is the tree. Can you understand the tree here?
Oh yeah.
Yeah. That's the rule that you use to predict.
Okay.
Okay, very good, Eunice. You did it. So how about others? Is it clear or not?
Thank you, sir.
Clear, sir.
Yeah. Uh, Amira, no problem?
Okay, sir.
Okay, huh? Okay, you did. Oh, so when you already did this, so that's the question now is, can you try if you use cross-validation option and then you use only training set option? Why they have a different result? So why if you use cross-validation option and the percentage correct is not 100%, but if you use training set option, you get 100% correct. And what's the difference between, say, for example, J48 and ID3? Anyone can answer that? Did you try? If you use cross-validation, how many percent? And then if you use the training set option, how many percent? Anyone want to share screen? So what happened if you use training set, the test option? No, the test option, not this one. Let me annotate. There, yes. And then you start again. Oh, if you use the whole training set, you get 100%, right? But if you use cross-validation, you get only 85. The question is why?
I'm not sure, sir.
Huh? When you use only the training set, that means 100%, okay, all your data is used for training. There is no test set. Okay, but if you use cross-validation, yeah, k-fold validation, that means you are actually divide the data into 10, right? And then use only 90% of your data for training, 10% for testing, and then repeat again 10 times. That's why the result is much lower, because you are not using the whole things for training and testing. Okay, and this is actually more robust. So the 85, okay, here is actually more robust than if you're using the whole data set using for training. Why? Because that 85 here representing if your data, okay, is only, if your model here is only used, okay, for, it has been validated, okay, and then you have new data set which is not in the data, then you can get up to 85% correct. Okay, if you use the whole data for training, of course you will get 100% correct. Yeah? But there is no test, right? So using cross-validation, basically you divide the data into training set and testing set. That is actually what we discussed today. Okay? So, yeah. So thank you very much for today. Okay, I will end this class.
Thank you, sir.
Yeah.
Thank you,
So,
sir.
can you read the slide for neural network? Next meeting, we will discuss about it.
Okay, sir.
Okay,
Okay,
sir.
sir.
Okay, bye-bye.